Ever wish you could be in two places at once?
Oh,
Well, in the quantum realm, that's kind of how things roll.
yeah.
Get ready to dive into the mind-bending world of quantum mechanics, where the very act of looking can change reality.
It's a bit like stepping into the Matrix, except this is real, and it's happening at the tiniest levels of the universe.
Today we're going on a journey through the history and implications of quantum mechanics.
Okay.
We've got articles and research papers that'll help us unpack how this field has turned our understanding of reality upside down.
And whether you're a physics whiz or just a curious mind, this deep dive will leave you questioning everything you thought you knew about the universe.
All right, let's set the stage. Can you give us a quick rundown of how this whole quantum revolution began?
Picture this. It's 1900, and physicist Max Planck is wrestling with a problem that's been stumping scientists for years.
Okay.
They're trying to figure out how objects emit light when they're heated.
Mm-hmm.
The existing theories just couldn't explain it.
So what was the issue? What were they expecting to see?
Classical physics predicted that heated objects should emit energy continuously across all wavelengths of light.
Okay.
But the experiments showed something totally different. It was like trying to fit square pegs into round holes.
And that's where Planck's groundbreaking discovery comes in, right?
Exactly. Planck found that energy wasn't emitted continuously, but in discrete packets.
Okay.
It was like discovering that energy comes in tiny, indivisible bundles, which he called quanta.
Okay, so instead of a smooth flow of energy, it's more like a staircase with distinct steps.
You got it. And that was a radical idea because it implied that energy at its most fundamental level is quantized. You can't have energy levels in between those steps.
Now, I remember reading that Planck himself wasn't entirely convinced by his own discovery at first.
Yeah, he thought it might just be a mathematical trick.
Oh, wow.
But then Einstein enters the scene and things really start to get interesting.
Einstein, the guy who already rocked the world with his theory of relativity, what did he bring to the quantum table?
Well, in 1905, Einstein took Planck's idea and ran with it.
Oh,
He proposed that light itself isn't just a wave, but also exists as these quantized packets of energy, what we now call photons.
wait, so light is both a wave and a particle. How is that even possible? It's like saying a car can be a sedan and a pickup truck at the same time.
That's the beauty and the bizarreness of quantum mechanics.
Yes.
Things don't always behave as we expect them to at the subatomic level.
Right.
And this was just the tip of the iceberg.
So it sounds like the floodgates were open at this point.
Right.
Were other physicists jumping on board the quantum train?
Oh, absolutely. Big names like Bohr, Heisenberg, and Schrödinger came along and added their own pieces to the puzzle, and things just got weirder and weirder.
We're talking about the idea of electrons existing in multiple states at once, particles behaving like waves, and a whole bunch of other mind-boggling concepts, right?
Exactly. These weren't just tweaks to the existing theories. These were full-blown paradigm shifts that shook the foundations of physics. Imagine going from a world where you could precisely predict everything, like clockwork, to a world where chance and probability reign supreme.
That must have been pretty unsettling for a lot of scientists at the time.
It was, especially for those who were deeply invested in the idea of a deterministic universe. I mean, for centuries, they had operated under the assumption that the universe was this giant, predictable machine.
But then quantum mechanics came along and threw a wrench into that whole idea, suggesting that at the subatomic level, things are far more probabilistic and uncertain than anyone had imagined.
It's like realizing that the universe has a secret set of rules that we're only just beginning to understand.
And one of the most mind-blowing of those rules has to be Heisenberg's uncertainty principle, right? Didn't that turn the whole idea of observation on its head?
You're absolutely right. Heisenberg's uncertainty principle is one of the most fundamental and counterintuitive concepts in quantum mechanics.
Yeah.
And it really shook things up.
So break this down for me. What exactly does the uncertainty principle say?
It basically states that you can't know both a particle's position and its momentum with perfect accuracy at the same time.
Okay.
The more precisely you know one, the less you can know about the other.
Hold on. Are you saying that just by trying to observe a particle, we're fundamentally changing its nature? That sounds like something out of a science fiction movie.
That's the essence of it. And it completely upended the traditional view of science as a purely objective pursuit. The act of observation itself was now entangled with the thing being observed.
One article we read used a fantastic analogy.
Right.
It said, a particle may have an exact place or an exact speed, but it cannot have both. It's like the universe is playing a cosmic game of hide and seek.
That's a great way to put it.
Yeah.
And this fundamentally challenged the deterministic worldview that had dominated physics for centuries. Remember, classical physics assumed that if you knew the initial conditions of a system, you could predict its future with perfect certainty.
But quantum mechanics essentially said, nope, not so fast.
Precisely. It introduced an inherent fuzziness, a fundamental limit to what we can know about the universe.
Yeah.
Even Einstein, who had revolutionized physics with his theories of relativity, really struggled to accept this.
He famously declared, God does not play dice with the universe, right?
Yeah.
He just couldn't reconcile this inherent randomness with his view of how the universe should work.
Exactly.
Yeah.
He firmly believed that there had to be some underlying hidden reality, some deeper level of physics that was still deterministic. He thought quantum mechanics was just an incomplete picture. This difference in views led to the legendary Bohr-Einstein debates, which went on for years.
So these were like intellectual heavyweight boxing matches with two of the greatest minds in history going head-to-head over the nature of reality.
That's a great analogy, and one of the most famous punches thrown in that bout was something called the EPR paradox.
Refresh my memory. What was the EPR paradox all about?
Well, in 1935, Einstein, along with his colleagues Podolsky and Rosen, proposed a thought experiment designed to expose what they saw as a flaw in quantum mechanics.
Okay.
Yeah.
They focused on the idea of two particles that had interacted in the past and then become separated, potentially by vast distances.
Their argument was that if you measured the momentum of one particle, you would instantly know the momentum of the other, even if they were light years apart. This seemed to violate Einstein's own theory of relativity, which states that nothing can travel faster than light.
So this instantaneous connection between the particles seemed to defy the very laws of physics that Einstein himself had helped to establish.
Exactly. This challenged the principle of locality, the idea that an object can only be influenced by things in its immediate surroundings.
Einstein believed that this spooky action at a distance, as he called it, indicated that there had to be some hidden variables, some unknown factors influencing the particle's behavior that quantum mechanics wasn't accounting for.
But then things took an even wilder turn when scientists actually started performing experiments to test these ideas, and what they found would forever change our understanding of the universe.
So they actually managed to test this spooky action at a distance in the lab. How is that even possible?
It involved a phenomenon known as quantum entanglement, and the experimental results were mind-blowing, to say the least. They confirmed that two particles, no matter how far apart they are, can be linked in such a way that they share the same fate. Measuring one instantly affects the other, as if they were a single entity.
Wait, are you saying that they actually proved that this instantaneous connection, this entanglement, is real?
Yes, and it dealt a significant blow to Einstein's hopes for a more deterministic universe. This was a pivotal moment because it demonstrated that our everyday understanding of space and time simply doesn't apply at the quantum level.
So even though we couldn't see or touch it, this strange non-local connection between particles was undeniably real.
This is where even the most skeptical minds started to question everything they thought they knew. The implications were profound, and it opened up entirely new avenues for understanding information, reality, and the very fabric of the cosmos.
Okay, so entanglement is real, spooky action at a distance is a thing. But what does it all mean? Does anyone actually understand what's going on down there in the quantum realm?
That's the million-dollar question. Even a century after the birth of quantum mechanics, there's no single universally agreed-upon interpretation of what it all means.
So all these brilliant minds, all these groundbreaking experiments, and we still don't have a clear answer. It's a bit like solving a complex puzzle only to find another even more perplexing puzzle underneath.
That's a great way to put it. It's a testament to how profoundly strange and counterintuitive quantum mechanics is. But that doesn't mean we're completely in the dark. We have a few compelling interpretations, each with its own strengths and weaknesses.
Okay, let's hear them. What are some of the leading contenders in this quantum interpretation showdown?
Well, the most popular interpretation, at least among physicists, is the Copenhagen interpretation, largely shaped by Niels Bohr.
I've heard of that one. It's the one that basically says, don't worry too much about what's really happening down there. Just focus on the probability.
Right, you got it.
Okay.
The Copenhagen interpretation suggests that a quantum system exists in a superposition of multiple states until a measurement is made. It's that act of measurement that forces the system to collapse into one definite state.
So it's like saying a coin is both heads and tails until you flip it and force it to choose.
That's a good analogy. But here's where things get really interesting. The Copenhagen interpretation emphasizes the role of the observer in shaping reality.
Wait a minute, are you saying that our consciousness is somehow involved in creating reality? That by choosing to look, we're influencing the outcome?
It's a mind-boggling idea, isn't it? And it's one of the reasons the Copenhagen interpretation is so controversial, but it's a serious interpretation, one that many physicists find compelling.
I've also heard about another interpretation, the many worlds interpretation. That one always makes my head spin. Isn't that the one where every quantum measurement spawns a whole new universe?
You're exactly right. The many worlds interpretation proposed by Hugh Everett III takes the idea of a probabilistic universe to its extreme. It suggests that every possible outcome of a quantum measurement actually occurs, but each in a separate parallel universe.
So there's a universe out there where I decided to become a quantum physicist instead of a podcast host. That's a bit hard to wrap my head around.
The many worlds interpretation is definitely a wild ride for the imagination. It's like saying that every time you make a decision, reality branches, creating countless new worlds where all the other possibilities play out.
Wow, that's heavy stuff. So we've got the Copenhagen interpretation with its observer-dependent reality and the many worlds interpretation with its infinite branching universes. Are there any other contenders in this quantum interpretation Royal Rumble?
There are quite a few, actually. One that has gained some traction is the consistent histories interpretation. It focuses on the idea that quantum events unfold along consistent, interconnected paths through time.
So kind of like a cosmic choose-your-own-adventure book where every choice leads to a different but consistent story.
That's a good way to visualize it. But even with all these different interpretations, there's still a lot we don't know. The fundamental mystery at the heart of quantum mechanics remains.
So where do we go from here? Is there any hope of finding a single satisfying explanation for quantum mechanics?
It's hard to say, but there's one particularly intriguing idea that emerged from all of this, and it has profound implications for our understanding of reality. It's called it from bit.
It from bit.
Yeah.
You're going to have to explain that one. It sounds like something a computer programmer would say.
It was coined by physicist John Archibald Wheeler, who believed that information, rather than matter or energy, might be the most fundamental building block of reality. Imagine that at the most basic level, the universe is made up of bits of information, like the ones and zeros in a computer.
So instead of atoms and quarks, we're talking about bits and information as the ultimate ingredients of the cosmos. My mind is officially doing backflips now.
It's a radical concept, but it suggests a deep connection between physics and information theory, two fields that previously seemed quite distinct.
It's like saying that the universe is a giant computer running on a cosmic code made of information.
That's a powerful way to think about it. And this concept of it from bit has actually led to the development of a whole new field of study, quantum information theory.
Which is closely tied to the development of quantum computers, right? The computers that exploit those strange quantum rules to perform mind-boggling calculations.
You're exactly right. Quantum computers harness the power of superposition and entanglement to tackle problems that are simply impossible for traditional computers to solve.
We're talking about breaking encryption codes, simulating complex molecules to design life-saving drugs, maybe even designing entirely new materials with properties we can't even imagine. The possibilities are truly staggering.
It's a rapidly developing field with the potential to revolutionize everything from medicine to material science to artificial intelligence.
So it seems like this quantum revolution is far from over. We've gone from questioning the nature of reality to potentially building computers that could reshape the future.
It's a testament to the power of human curiosity and the endless surprises the universe holds.
Well, after this deep dive, I think it's safe to say that reality is a lot stranger and more wondrous than we ever imagined. Who knows what incredible discoveries await us in the future? For our listeners out there, if you want to explore further, look into the quantum Zeno effect. It's the idea that observing a system can prevent it from decaying. Truly mind-bending stuff. Until next time, keep exploring, keep questioning, and keep diving deep.